So then I want to introduce to you Henning Rehn. Henning is a physicist and optical engineer with lots of experience in R&D management and optical design. He used to work as a team leader of the Optical Design Group at FISBA, but at the beginning of this year, Henning funded Illuminatio Solutions, where he continues his work, and he now works as an optical designer and owner of the company. Henning, feel free to share your screen, and the floor is yours for your presentation on measurements in the phase space.
Yeah, wonderful. First question to the audience, do you think in my company there is a letter missing? But I have to say, no, there is no letter missing. Illuminatio is Latin and means enlightenment. So I choose to go the path for enlightenment, and I hope it will work out in the end. Okay, today I want to talk about the phase space and how we can measure quantities in the phase space. And this is my outline. So of course, I first have to introduce the phase space and some diagrams we can draw and show some Étendue calculations. But then I go to, say, difficult cases where we cannot apply the standard Étendue theory and have to estimate Étendue anyway. Yeah. And then I go to other measurement things by filling the phase space with light and show you how we can measure some quantities. And then I come to really crazy things such as a fuzzy source or a fuzzy target and what we can do there. So, okay, let's start. A ray is in illumination optics. We catch the ray by a screen, which is just a surface in space. And we have local coordinates on the screen, X and Y. And the ray is described by two angular coordinates. So the family of rays in illumination is described by four coordinates, or in other words, the ray is a point in a four-dimensional phase space. So four-dimensional is not really a practical. So we try to say do some cross sections. We can here at left. I have shown you a spatial cross section with the X and Y coordinates. And you can see, for example, the surface of an LED. Then we have an angular cross-section. Both diagrams are in the phase space and they are obvious, but they are not so exciting. But it gets very interesting if we do some plot with a spatial coordinate and with an angular coordinate. And again, I don't use the angle itself. I use the angular extent, or the quantity which is conserved in refraction. This kind of diagrams I call phase space diagrams. So the phase space diagrams come in two flavors. We may have a meridional section through our system, and then I have a local coordinate, maybe X in this plane, and I have a optical momentum or this angular definition on the y-axis, and my ray is just a point in this diagram. In other cases, it's reasonable to say discuss the rotational symmetric case, and so I have a beam with a source plane in the coordinate r in this plane and a target plane in the angular coordinate theta. And this is the other way to do diagrams in the phase space. So if I have more than one ray or a whole volume in this phase space, I introduce the name Étendue. So this is basically a beam which is described by some area on the screen and by some angular range or extent. And the whole thing is described by, say, a volume which is called Étendue and is written on bottom right. So Étendue is integrated the phase space about solid angle and area. So this Étendue extent, if I put this in my phase space diagrams, I might get something like those green rectangles. So this is a certain range in the spatial and in the angular extent. Or I can have it on the right in the rotational symmetric diagram in the radial extent and the angle. So these are plots of Étendue in my phase space diagrams. And so we are still absolutely talking on geometry only. There is no statement whether there is light in the Étendue or not. This is not yet discussed. Okay, let's go on. Optical elements or systems may be described as transformations in the phase space. So here I have a very simple condenser system with or 2F system where I have a distribution on my object plane or source plane, which is described by this distribution in the phase space diagram. I have put a red dot on the corner in order for you to be able to identify this. Then I have a little bit free space propagation, and my phase space diagram is shared a little bit. Then comes a thin lens. The phase space distribution is once again undergoes a shear, and then I have another free space propagation, and I obtain a final distribution, which is a transform or transformation of my initial distribution. So this is for the very simple case, and we can have a systematic of all possible phase space transformation, which we found in a book by Kurt Bernardo Wolf from 2004. And yeah, he uses the variables in a different way than we do, but it's the same statement. So he, based on Lie algebra, he developed a system of all possible phase space transformations. On the left, we have the order. So for first order, we have free space and lens effects. Then come, for example, third order, you see all the Seidel aberrations, and you see some effect called POCUS, which is only very occasionally described. And then you have also phase space transformations of second grade and of fourth grade and fifth grade and so on. And we have some intersection here with the theory of imaging, but there is much more. Okay, let's go ahead, and we fill the Étendue with light. So now we have some rays inside our Étendue, which are given some energy, and so in the end we have light in the Étendue. In the phase space diagram, it looks then this way. So I can take light of constant luminance. So I would fill my Étendue constantly. Either type of diagram. But it doesn't need to be constant. I can have a variable luminance. Luminance can vary with space or with angle, and then I get a distribution of luminance in the phase space, which you can see here. This is basically the general case, and this is the basis for everything we do. If we start to measure light, and we can do this, for example, if you want to measure illuminance along a spatial coordinate, we integrate over all angles. This goes along this interval, and we sum for this spatial coordinate and get an illuminance value. This is basically the projection of the distribution of light in the phase space, and we obtain illuminance distribution. Important, for example, if you have inhomogeneous sources. There you can do that, or basically the camera did what I am explaining here. The same can be done for a projection into a certain direction, which is indicated by the horizontal arrow and the horizontal interval, and then we get a certain intensity value. So this is measurement of light in the phase space. So this is for introduction and for the ordinary cases, and now we go a little bit deeper. So Étendue in the phase space. So if we have a limited volume in the phase space, we can apply some very wonderful formulas. Julius had already presented some of them. For example, in the rotationally symmetric case, if I have a circular, source where every pixel emits into the same angular cone, then I can apply this formula. Étendue is n times pi times radius times sine of theta squared. The same if we don't have a rotational symmetric case. In case of an imager, this is area times n sine of the angle squared, and here times the area. In some cases, the angular distribution of every area element on the source may not be given by a certain angle, but by a kind of an exit pupil, which is shown here in this diagram. This defines a light tube, and the étendue of a light tube is given by Hottel's formula. This is originating from the 60s and comes from the thermal radiation field. And this describes the étendue of two rotational symmetric disks facing each other. Okay, so far, wonderful simple cases, and we can calculate everything. But in some cases, if you have, for example, a source which is clearly not defined, like an LED, by a hard boundary, but is somewhat fuzzy, what do you do? Or if you have an optical system with a kind of a source, a target, and something strange in between. And of course, you can solve this by integrals and sitting for a week and writing all the boundaries of the integral here. But if you are sitting in a negotiation with your boss at your side and the customer says, if we can get 100 lumens, you have the project, then you need to do it fast. And I want to show you a way how to calculate étendue for such cases. So let's start with the source. If you have a fuzzy source, what do? We apply a phase space binning. So basically, we split the phase space in maybe a few hundred spatial bins and a few hundred angular bins. And then you can measure the flux or the energy in every bin. So you can, for example, do this if you have a ray file of such a source. You can just bin all the rays you get and measure energy. And then you look all the 10,000 bins you have from your source with the flux, and you sort them by luminance. Or if they are equal, of equal étendue, then you can sort them by flux, and then you get all those bins. And the next plot derived from this one is you make a cumulated plot. This is the first bin, this is the first and the second, and the first three bins, and so on, and then you get this kind of diagram. And in the you end up with a plot of certain sources, which looks different and is very, very useful. I have here in this luminance diagram, I have on the x-axis, I have the étendue, and on the y-axis, I have the flux. And if I plot my cumulated information for a certain source, for example, the blue curve is a white LED, then you get this one. And if you now come with a certain collecting étendue or target étendue, you can just take the information, how much flux you can get at maximum for this target étendue. For example, for this value, 0.6 millimeters d radian, you can get from the white LED maybe 170 lumens. And by means of this diagram, you can pretty good compare different kind of sources. For example, in comparison with the white LED, you can look at a laser phosphor solution, which shows obviously higher flux for smaller étendues. So for the same target étendue, you could get maybe 230 lumens. So for the application of a product development, this means for small étendue, the laser phosphor source is better. For large étendue, the LED will be better. And that's an answer the colleagues want to get. By the way, the slope of the curves is the luminance. And one more comment is this diagram is showing an upper limit for collecting flux. It does not prove that you will really find a solution which will give you that limit. Okay, let's go forward. And now we look for the non-trivial systems, crazy systems where you have to find out or calculate the étendue. So on the left, I have taken this nice figure from the internet. You can see the reference here, which shows we have just some irregular set of phase-space cells which together define the étendue of the application. Yeah, and to calculate the étendue of this thing, we do a very simple thing. We fill the étendue with light, and we simply measure the flux. And then we can very easily calculate the system étendue. And this is done by very simple steps. So I have my crazy system. I have a source of constant luminance. And I have here on the rear, I have a receiver. And I set it up. Yeah, so I need, of course, a model of my optical system in Siemens or Lighthouse or whatever. Yeah, I put here where the source location is. I put a Lambertian emitter, and then I put a receiver on the target, let it run, and I measure the flux. And then, pretty easily, my system étendue is given by the ratio of target flux and source luminance. Very simple. So, and we can do this for absolutely crazy situations. Look here, I have a source on the left. I have a partial absorber. This is again a slit or an aperture. Then I have a scatterer, and I have my target. Yeah, and again, I get a certain, I measure a certain étendue value, and this lets me to give the statement étendue is what we measure. the method is absolutely agnostic about whether scattering or absorption is allowed in the system or not. I simply measure, and what I get is Étendue of the system. Okay, one application I want to show you. Imagine a situation, I have a light source and I have some primary optics. I have shown you a CPC here, but it could be whatever. And unfortunately, the light sources come with a very thick cover glass. There might be different reasons. I think the LED manufacturers are afraid that we, as the customers, would destroy the bond wires or whatever. I don't know, but sometimes you are really faced with a very thick cover glass and have to take this into account into optical design. And if you do lens design, then you will very soon learn that is not helpful. Okay, so we want to apply our method to understand the effect of a thick cover glass. So for this purpose, we define a light tube. And in this light tube, you see the characteristic rays. So the blue one, the upper blue ray, is a marginal ray, which goes from the center of the source to the edge of the target. And this green guy is a chief ray, which goes from the edge of the source to the center of the target, and so on. We can calculate Étendue, as I have shown to you. But now we want to put some medium inside the light tube. So we can either put it here where it covers maybe 90% of the volume, or later we will see 50% or whatever, or we can define the ambient as a medium. So we put the whole light tube in a medium. So let's look what happens. We can calculate this analytically. So using Fermat's principle, I can calculate my marginal ray and where it goes by simply varying this intersection point here. And by taking these obtained rays into account, I get a formula which is under some assumptions is given by this formula. So here you have the both sides of the light tube. You have the distance, and then you have the thickness of my medium inside the medium. So I will show you at the end of the talk, I will show you a reference where we have published the whole thing. So if I do this, I can estimate some Étendues. So here I have an example. I have a 1 square millimeter LED on the left. I have a 1 square millimeter target on the right. I have 2 millimeters distance. And now I derive some Étendue values. So for the source, of course, we have pi square millimeters d radiant. If I have the 2 millimeter distance in air, the Étendue is pretty small, 0.22 square millimeters d radiant. And if I embed the whole system in a refractive index of 1.5, then I think Jules had shown this earlier today. We have to simply multiply the Étendue by n squared, and I get 0.53 square millimeters d radian. So by our glass formula, if we let the thickness of the glass inside approach 1, and I use everything here, I got also very accurately 0.53 square millimeters d radian. So then I took light tools and I measured the Étendue by simply putting a certain luminance here and measuring the flux here. And in air, I get 0.21, which is pretty close to this calculated value. And with a glass block inside, I get 0.48. which is similar to this one. Of course, if we now would discuss all the involved approximations, we would probably very well understand this tiny difference, but basically is what we measure is the same as we calculate, but the measurement goes probably much faster. Okay, so now final comment on targets. If we have an hard-edged source and a fuzzy source, or maybe we can have a hard-edge target like this one, and we can have a fuzzy target or maybe a receiver with a weird optical system, which has to be described like a kind of a angular dependent sensitivity or something like that. I want to show you one example. Years ago, I had to deal with a DLP projector, and the question was, how should I shape the reflector and the distribution of light inside this integrator rod? It's going all, I'm sorry. It's going all the way to the left through this rod, some optics, some prism, the DMD and projection lens, and I measure light on the screen. So here, first I can apply the method and measure the étendue of the projector, which may be a little bit different of the étendue of the DMD itself, yeah, by simply sending light of a certain luminance inside the rod and measure on the screen. So here is my rod entrance, and I have a source defined in the software, and I can get the étendue of the projector. And it turns out the étendue of the projector is a little bit smaller than the étendue of the DMD. So there is some étendue lost on the way, and later we learned that the angular transmission is not constant, but it's decreasing for higher angles. And so in the phase space, I could somehow show a sensitivity distribution in my projector étendue, which could maybe look like this green spot here on the right. The good thing is that we were able to optimize the lamp shape on this curve and got a much brighter, or we got more luminous flux than with earlier methods. So we're coming to an end. Yeah, if I have a complicated source, I usually describe it by array file. If I have a complicated target like this AMS sensor, can I describe it by something similar, like a sensitivity distribution file or whatever? I don't know, but maybe we can think about it. Okay, for summary, we can handle objects and systems and estimate their étendue, or we can measure even for the irregular shapes or strange systems. And for my example with the cover glass inside the light tube, we found out that the étendue is the same for an almost filled light tube or a completely embedded light tube. And so in conclusion, this means the cover glass does help us. It would be much worse if we had an airspace with the same thickness than the cover glass. And I could only show some first ideas, and if we look deeper inside, this is again connected with the angular extent, and everything plays together, and we have described this in a book, and we are just proofreading right now, and we are hoping that will appear in 1 or 2 months. I'm not sure, but this is under preparation, almost done. Okay, with that, I want to thank you for your attention, and looking for questions.
Thank you, Henning, for the presentation. I have a question on the fuzzy distributions and the phase space binning. How do you determine the binning accuracy? And then on the plot that you showed later on, for the different types of light sources, did you use the same binning for all three of them, or did you fine-tune according to the source characteristics?
You mean this one here? So
Yes.
you may imagine you get the source in terms of a ray file, and then you I think every or most of us illumination engineers did program some kind of ray file analysis.
Mm-hmm.
Then you use a fine binning and do maybe 10 or 20 bins per coordinate, which will give in the end 10,000 to 40,000 bins, and much more you cannot handle. And then this is practical, and then you can calculate, say, theoretical maximum values for light collection from such kind of a source.
Okay, thank you. I believe in view of time that yeah, we need to close here with the presentations. Thank you, Henning, again, and also thank all the other speakers for the very nice presentations.